think the best way to describe it is it's inspired by physics, because there's over the full process there's no human step involved. And I think also one of the questions I saw passing by is, do you need a database with existing solutions or pre-calculated solutions to make this happen? The answer is no.
Welcome to a new episode of the Engineered Mind podcast. I'm your host Jousef, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very excited to welcome Lieven Vervecken, CEO and initiator of Diabatix, to my show. Diabatix is mixing AI and machine learning with generative design, optimization and traditional CFD methods to design a new breed of AI-driven heatsink designs. In this podcast, Lieven and I talk about pain points in thermal heatsink design that are solved using the tool Coldstream 2 to effortlessly perform thermal analysis, heatsink selection, and generative design in one powerful platform. Lieven explains optimization techniques and how they are implemented inside of Coldstream to enhance engineering workflows. We will also cover how to set up a simulation from beginning to the end. Lieven will also talk about topology optimization, a bit of the theory behind it, and how users can get the full experience of this powerful technique, and much more. If you would like to support the channel and podcast, make sure to give this episode a like and leave a comment down below. Subscribe if you haven't already. And now, ladies and gentlemen, here is my podcast with Lieven Vervecken. I think we can just casually start talking. I'm not sure how these live podcasts go, Lieven, but anyway, welcome to the show.
Thank you, Jousef. It's a pleasure being here.
Yeah, there was kind of a ride, no pun intended, this morning, right? You come actually from Belgium, right?
Yes. So it's on paper an hour and a bit drive, but in practice it was close to 2 hour drive.
Yeah, I also underestimated the time it takes to actually get here. So I woke up at 8 or 7:30, prepared, said, let's take it easy with the breakfast and things like that. Then I came here at 9 and then things didn't work, as always, like Murphy's Law, as I told you before. Yeah, it's horrible. Let's just hope the audience likes it. Let's hope for the best.
Yeah,
anyway,
let's see it.
First live podcast, Lieven. Thank you so much for being here. Today we'll talk about AI-driven heatsink optimization and heatsink design. Can you talk a little bit about what you do, what your background is?
Yeah, definitely. And I do know a little bit about that topic. So maybe let's first start with my background. So like many of your followers, I'm an engineer. I have a very engineering background, so to speak, because I have a mechanical engineering degree. On top of that, a nuclear engineering degree, and then did a PhD in fluid mechanics. So I've spent almost 10 years at the university to get to the point where I am now. And then right after obtaining my PhD, I started Diabatix. And from day one, the focus of the company was on helping other companies with thermal design. And along that process, we developed our generative design technology or topology optimization techniques that we apply today, which we typically market as AI-driven design for cooling components.
Mm-hmm. Before this podcast, Lieven, I've looked up something, maybe you've heard of it before, that there was a story of the Xbox 360. Mm-hmm. There was something called the red ring of death. There were some overheating issues, and clearly there is a need in the market for actually designing heat sinks and getting rid of the heat inside of components. You also heard about the Apple scandal, I would call it. And then there was one guy saying from actually the Xbox team, they lost $1.15 billion just because of this heating problem. And clearly you can see that heatsink design is a needed topic. So how do you tackle such a problem in the first place? You know that something might be overheating. How do you tackle such a problem, maybe even with your platform?
Yeah, it's definitely a hot issue. Huh? No pun intended. But the first hint we got from it is as soon as we started Diabatix, it took us, let's say, a year and a half to develop our core technology, and then we went live with a very basic website. If I would look back at it now, I'm pretty embarrassed about the design and everything. But within 1 month it was live. We actually had somewhere around 5 or 6 huge multinational tech companies who became a customer.
Wow.
So that was the traction we immediately got was impressive, and was immediately from 3 different continents. So. It was going from Silicon Valley up to Japan and some countries in the middle as well. So we immediately got a confirmation that what we actually started doing is solving a problem in the industry. And the way we solve it is, the primary issue that we found in the whole thermal design cycle process. So when an engineer starts to make a heatsink, the main limitation of the final performance is actually the first step that engineer takes. So all the tools that are existing in the market start from the premise that you need to have an initial design. And that design is created by the human engineer, typically from a copy-paste of a previous component or previous product version. He parameterizes a number of parameters or dimensions inside the component, optimizes those, and then you have in their version an optimized design. But from that perspective, you basically fix the final performance you can reach with the first design that you make. Because if you start from something with pins or with fins, you will always end up with the same pins or fin shapes. Might be more, might be less, but you won't switch to a completely different shape. And what we managed to do with Diabatix is create a technology that you don't need that first step. We can actually design a cooling component starting from scratch, so you don't need that initial design anymore. And it's actually our software that will search for the most optimal shape to start from, to start the optimization process from. And that initial shape is typically wildly more complex than what you would be able to design as a human engineer. But at the end, your performance gains in the order of 20-25% become feasible then. And that's the added value we bring.
Mm-hmm. Would you say we can call it human-inspired generative design? Is that something in this area where we can say it's basically inspired by humans, the algorithm is inspired by humans? Or would you say humans are inspired by nature and then design?
Well, it's actually, I think the best way to describe it is it's inspired by physics, because there's, over the full process, there's no human step involved. And I think also one of the questions I saw passing by is, do you need a database with existing solutions or pre-calculated solutions to make this happen? The answer is no, because the whole process starts from just a whole series of CFD analysis, which generates a huge amount of data. So typically when we generate one component, and over the full process, it generates in the order of 5 to 10 terabytes of data, and it's by processing that data and the information contained in the temperature fields, the turbulence, the velocity fields, etc., by combining all of that information, that we actually make a new and a better design, or that the system knows which changes to make. But it's all driven by basically the Navier-Stokes equations.
Interesting. I was wondering, when an engineer, like the average engineer, they usually, I don't know, maybe you know it better than I do, they would start with an Excel table, maybe some hand calculations. Yeah. How was it? Maybe can you compare the workflow before Diabatix existed, now when Diabatix existed, how it can, let's say, augment engineering workflows?
Yeah. Well, I can give an example of one of our more recent customers. I'm not going to name them, but they describe the process that they have in place pretty accurately. So, because we always ask it in first call or first chat we have with potential customers, we always ask, okay, can you describe how you do it now? And we were talking to the simulation engineer, who was basically in charge of evaluating the designs that his colleague generates for him. And when I asked him, okay, so how do you do it today exactly? And he said, so we have a guy and he has an Excel, and after a few days, when we give him a set of parameters, it spits out a number of optimized parameters that go to another guy who has an AutoCAD. He draws the heatsink design in, or integrates those pins into a bigger component, or fin shapes into the bigger component. And once he is done, that goes to me to evaluate with CFD analysis and whether it worked or not, the component. And 9 out of 10, it doesn't work. So the cycle starts over again. And so the feedback is given again to the guy with the Excel. Please make me another set of parameters. That goes to the second engineer who draws it then, and then again to the simulation specialist. And that cycle goes on and on for typically 2-3 months, up to the point that they have either a working solution, or in this case, and that's the point that they came to us, they didn't find a working solution. And then they basically start using Coldstream and we show them how you can actually do it in one step. Now, in this process, it's the one that I described now. It's probably the most extreme example that we found. I mean, it was with 3 different people involved and a very inefficient workflow. But in practice, 9 out of 10, there's at least more than one person involved, someone who draws the component, one who analyzes the component. And what we actually do with Coldstream is we give either one of the 2 engineers the power to do the other one's job. So when you're a design engineer with Coldstream, you actually have under the hood all the knowledge, knowledge and the requirements that you need to do an accurate CFD simulation. You have that available to you with a few clicks of a button. You basically enable those simulations into the design process. Or for the simulation engineer, when he would use Coldstream to design a component, he can simply select the manufacturing technique that he wants from a library of parameters that are all pre-configured or that he can extend himself. And basically, that way, he can generate the CAD files that normally his colleague would be doing for him. And in that combination, we actually make the process much more efficient. And we don't exclude any of those people, but we actually make the jobs of any one of them more interesting. So for the CAD engineer, for instance, instead of having to make 5 or 10 or 15 different variations of the same component, basically with a few clicks of a button, he can generate the component which is most likely to work for the situation that is and the boundary conditions that are given. And once that component is ready, it goes to his simulation expert, who can then do a whole series of transient analysis and more advanced FEA analysis and structural things to verify whether the component meets all the criteria, which some might not be able to be taken into account by with Coldstream, for instance. But the job of both engineers suddenly becomes much more interesting when they start using Coldstream.
Yeah, very interesting. I like that you say we don't substitute engineers, but we augment or enhance their workflows, which is really, really nice. I was wondering, when we talk about ROI, what do we talk about in terms of time and money savings for the company or different companies that you've worked with?
Yeah, it varies. It varies a lot about. It really depends on the application. So for some applications, time savings are expressed in terms of engineering time, and then reduction from 3-4 months for the design of battery cold plates to 1 or 2 weeks. That's something we basically do on a daily basis. On the other end, we have a very big customer in Silicon Valley who uses it to optimize the cooling for their supercomputers. And there, the saving, if you save on cooling, on the cooling requirements of a few percent, for them it's a saving of millions from there on over every year. So in power consumption reduction. So the saving is for us very difficult to quantify, but what we charge the customer is very easy. It's a subscription plus the computational time you need on our platform. So you're not paying for Coldstream if you're not using it. That's the basic principle for us.
Pay for what you use. It's pretty
pretty
neat. Can you walk us through a workflow, maybe in Coldstream? How does it work?
Yep.
Maybe if I start up, I know I'm an engineer, I log in. How does it work from the start?
Yeah. Well, you basically get if once you get an account, it's pretty easy. Maybe to explain why I will probably say it's pretty easy. There's one very important reason why it is. Our head of product, Roxanne, she's one of our brilliant people in the company. She's actually in charge of the full design and the workflow of Coldstream, but she has a PhD in optimization. But actually an engineering degree in architecture. Mm-hmm. She has never seen a CFD tool from the inside out, and the same with a CAD tool. The moment that she started with developing Coldstream, she had basically a clear mind on how a tool like that should look like. And she has done, in my opinion, a brilliant job, because the way it looks is you log in, you see the whole interface is pretty intuitive. If I would show it to you, probably in half an hour, I've explained everything you need to know to get started. And the starting point is pretty simple. It's the same as what you would have to give to your colleague when you would ask him make me a heatsink or design me the cooling for this product. So he will first ask you what is the CAD file. So you need to upload geometry in the step format, and then you will ask me, okay, what are the boundary conditions? And you will probably have to give for every component. You will have to set the material. You have to set, is there a heat source or is there an inlet with a certain flow rate or something like that. So that's pretty common, I would say. You have to set the boundary conditions the way you would set them in any CFD related tool. I mean, from that perspective, we're not that different.
Yeah, I was wondering, Lieven, sorry for interrupting. Is it like that you give a geometry in form of a bounding box, like you give it the domain, or is there already a heatsink in the design? Probably not.
No. So there's no heatsink in the design, but what you need to do is you upload your geometry. Typically, it's an assembly of many different components, and within that assembly, we ask the user to indicate the design region, to indicate a design space. So it's basically an additional body somewhere, which is just a block or a very complex shape, where we can then say, okay, or where the user can then say, okay, this shape is actually the space I have to create a design. And within the platform, it will also be asked, okay, what is then the material type of that shape, and what is the manufacturing that you want to apply for that shape. But the user does need to identify, okay, within this space, the software can change something. All the other parts are not touched, but they will be there to make sure that the simulation is accurate enough to make such a design. But things like meshing or the more complex wall boundary, the wall layer modeling and stuff like that, all of that the user doesn't have to care about.
That's really cool.
Yeah, because the advantage that we have is we have very clear focus on thermal, and it makes that you can automate and that you can basically they can automate basically everything in the backend for those kind of applications. So don't expect to be able to calculate hypersonic flows accurately with Coldstream, because they're simply not relevant for cooling. So it's not in there, and by leaving that out, we can actually simplify a lot of the other things.
I see. When it comes to post-processing, is it also directly integrated into the platform? So an engineer would immediately get a feedback loop of, maybe I should change a boundary condition or make some tweaks here and there?
Yeah. So what we did there is, before we launched Coldstream, because it's actually a fairly recent product, because we only launched it a year and a half ago. But the 5 years before that, what we actually did was, to survive, was actually sell services to our customers. So we would use our draft or alpha version of Coldstream just in-house. And we noticed that customers were always asking the same things in the reports, and they were always asking the same tables, the same overview, the same graphs, the same 3D plots. And what we did with Coldstream was we didn't make it an active post-processor, so you won't be able, if you see you can visualize all the results, but you won't, for instance, be able to actively create slices or clips or change the zooming at certain detailed level or sample points. All of those things you won't be able to do, but what you will be able to see is a whole set of pre-digested information that if we now would do services, we would just copy-paste the tables that you see into the report, and then the report is done. So also there, from engineering point of view, you save a huge amount of time because everything is pre-calculated. And if you do need more detailed insight into the simulation, you can just download the raw data. So we give all the data available in VTK format, so that everyone can process it in ParaView if they want.
That would have been my next question, so you answered it already. Pretty neat. I was wondering, maybe from a mathematical point of view, you said in the beginnings you did your PhD around that topic, so it would be interesting for me, like, what is topology optimization all about? Maybe you can explain maybe from a mathematical point of view, and also is there like the optimal algorithm? And obviously you can't talk about the Coldstream algorithm for sure, but maybe what you've made use of in terms of like the advantages of such optimization algorithms.
Yeah. Maybe a small side remark. I didn't do my PhD in this topic. So my PhD was in the field of fluid mechanics. So I did a PhD in the field of basically it was simulating the dispersion of radioactive gases. It was in the context of nuclear safety.
Yeah.
But the skills I had was I was able to simulate things very accurately and setting up cases setting up simulations in a very efficient way.
Mm-hmm.
My co-founder Joris, he had a PhD in thermal modeling, and what we actually did was putting the pieces together, and then on top of that, we had the skills of being able to read scientific literature and interpreting papers, etc. And then we saw the topology optimization techniques passing by, both density methods and the shape optimization methods, the level set methods, and we put everything together into a configuration where we believe now it's the best way to do it, and that's the only way to make it work in an industrial context. But the fundamental basis of any of those techniques is basically the starting point is not. It's not like the classical artificial intelligence where you start from databases of information or designs that are ready, because what we think, can't prove it, but what we think is if you start from databases filled with pin heatsinks and fin heatsinks, you will never end up with the shapes that we generate, because none of them look like pins or fins. So we had to start with something else, and that was for us the primary reason I had to go towards the topology optimization methods, which basically start from just the Navier-Stokes equations in the most pure form, and depending on the method that you apply, they use different ways to calculate what you then can call a sensitivity or a gradient with respect to your design. It sounds maybe a little bit mathematical, but basically what it does is if you imagine that you have your heatsink, and you would imagine every point in space being one of your design variables. If you would mesh it, it would correspond to a mesh of, let's say, 10 or 50 million cells or something like that. Basically what any of those methods do is result in a gradient that will indicate whether that point in space needs to be solid or needs to be a fluid. And if you repeat that analysis 50 or 100 or 1,000 times, and you use a smart optimization algorithm, then you end up either with a Picasso kind of looking thing, or you end up with a decent heatsink design. And it took us about 2 years to not end up with Picasso designs, but end up with decent heatsink designs.
Interesting. I mean, how does the algorithm decide if something should be solid or fluid?
It's typically a combination of a few things. So on one hand, it's a combination. Well, typically it's a combination of either the objective function that will probably make everything solid if your objective is to make it as cold as possible, because then your optimal is getting basically a solid block, and then you have the highest conductivity, but your pressure drop will be infinity because your fluid cannot pass anymore. But on the other hand, you have constraints like a pressure drop constraint, for instance, that will probably want to make it as open as possible. And then it's the role of those optimization algorithms to find the balance between making enough channels so that the pressure drop is met, but don't make those channels too big or too small, because else your temperature constraint or your temperature objectives won't be met anymore.
Got it. I was wondering, when we announced the podcast, Lieven, it was all about AI-driven heatsink design. Now, everyone is wondering in the podcast, what is this AI thing called about? Sometimes when we talk about AI, people mean linear regression, but probably the secret sauce is more than linear regression. Talk, obviously know how to talk about it, not give away too much. What is the secret sauce? How does it look like? Is it more than just linear regression?
It's definitely more than just linear regression. Yeah. So I think so in essence, what we do is it really depends on who you ask. So, and of course in marketing terms, AI has been a buzzword and still a buzzword, and you would be a fool not to use it yourself if it's valid to be used. So we basically jumped on that train as well, saying that what we do is actually AI-driven design, and there are many different ways of looking at it. But when I give a talk, I typically say is, we do with Coldstream, it does the job of a human at the same level or better. And that makes it, on the one hand, intelligent, because you do the job of a human engineer, and on the other hand, it's artificial because it's not a human doing it. I mean, it's a computer doing it. If you talk to a mathematician, then you basically say, it's a set of algorithms and tables and statistics that are filled, and at a certain moment, it sees the direction in which a design needs to go, and it follows that direction. So it really depends on who you talk to. But in when I speak to engineers, who are then typically in between the both, I just pose them the following problem. So imagine that you have an optimization problem, and you have 1 or 2 or 3 variables that you want to optimize. That's pretty straightforward. You just sample so many variables. Now imagine you can sample each of them like 50 times or 100 times, and depends on the cost of your model, but you will be able to find, by sampling, you'll be able to find an optimum. Now imagine that instead of having 3 or 4 variables, you have 3 million or 4 million variables. At that point, you won't be able to sample each of the possible combinations anymore, because you will end up with trillions and trillions and trillions of combinations, but you will have to use gradient-based optimization algorithms. That's also our starting point. Now, on top of that, imagine that gradient, instead of producing one vector, you actually produce a whole series of vectors, and on top of the gradient also temperatures and velocity profiles, etc., and also gradients of all the constraints that you have. You end up with not one vector, but a whole list of vectors. If you would like to put that in one optimization algorithm, it needs to be able to process, as I told you, in the order of 5 to 10 terabytes of data in a very efficient way. And to be able to do that, that's a challenge. And that's a challenge that we solved with Diabatix. So we basically managed to spice up the optimization algorithm with basically machine learning techniques and AI techniques to be able to process that amount of data in a very efficient way.
Got it, that makes sense. I was wondering, did you start from scratch? Obviously, you put a lot of energy and effort into developing what we see today as Coldstream. But did you start from scratch, or did you use existing packages to build on top of them then? Yeah, we didn't reinvent the warm water. So, no. So, starting point, and that's like a public secret. Starting point for us was using OpenFOAM as a simulation library. So we did develop a whole set of libraries ourselves. Also, the solver is a fully customized solver. It's probably closest to what you have with the CHD multi-region foam solver. That's probably for some will ring a bell. But yeah, that's a full customization thing. Then we coupled it as well to a CAD engine, so to be able to make step files within the tool itself. You have the optimization part, you have then the intelligence part, and then on top of that we wrote a full layer of code ourselves that connects the dots, and that's only what's happening in the back end. Because then Coldstream itself, that's in the front end, that's a whole other set of software tools and codes and public libraries that we combined to make it work as well. So we try to reuse what was available, just from I think it's just decent way of working when you're a young small company. It managed to keep our core team size fairly small, because we're now at 10 core developers. But next to the things that they do, basically we have a whole external team of developers that all are developing their own software, that as soon as they have a release or that they publish an update, that we basically pull and then we update that part of our software as well that way. So the developers of OpenFOAM, for instance, are basically on a daily basis contributing to what we are doing as well. I see. Okay, interesting. I was wondering, when it comes to the manufacturability of components, because I've seen some fancy designs that you generate on the website and so on and so forth, and I would, as an engineer, never design something like this. It looks very fancy. First question would be, is this really the optimum, or like do some engineers think maybe I could be still better than the optimization algorithm? And then also, is it manufacturable? And also when it comes to the manufacturability constraints, can they also be fulfilled?
Yeah. So we cannot prove that this is optimal that we find. Typically, we say, we're the only ones with this technology in worldwide, so it is the global optimal. But that we cannot prove. So, but from our experience, what we have noticed is we have a few tweaks or a few parameters that we can tweak that would result in different shapes, sometimes very similar shapes, sometimes very different shapes for the same set of boundary conditions, for the same optimization problem. So we know we not necessarily find a unique solution with Coldstream, but what we have seen is that all of those solutions are, from performance perspective, very close together. So our understanding of the global optimum is that it's more a plateau. I think it's an English word, So than one single design, which is the best in all situations. So there are multiple. We believe that there are multiple designs which can be completely differently looking, which would result in a very similar performance. And with Coldstream, you find one of those. But we cannot prove that it's the ultimately the best one. And sometimes it happens that you see the design that you then say, okay, maybe if I make here a small manual change, it might improve slightly. Sometimes it happens, and sometimes it makes it worse. So then that's very difficult to put a finger on what to do best there. So typically we don't touch those designs, because if you gain, let's say, I'll put it this way, if you compare to a reference design, if you gain 20%, whether it's 18% or 21%, you couldn't care less at that moment anymore. What's much more important is the second point you highlighted, the manufacturability. That was a challenge for us to make sure that the designs are manufacturable. And that's probably the part where we have put the most effort in over the past years in our development, is to make sure that if we design something, that it is manufacturable over a whole set of parameters. Because we do give users the capabilities to enter their own set of parameters, but you do need to make it robust then. And you do need to take into account that users sometimes enter wrong data, and even then, for their wrong data, should still result in something which is not manufacturable, but not manufacturable within the wrong set of parameters. So it just needs to work always. Did the last one make sense?
That made sense. Yeah, I was wondering though, in terms of parameters, like, do you also suggest to users if the data they are putting in is maybe not valid? So we have a whole set of pre-configured manufacturing techniques to show, this is actually how you should enter it. And there are a bunch of validation checks done before any design case starts. Because a design run, depending on the complexity, can take a few days or a few weeks, and you don't want to see after 2-3 weeks that you made an input error. So before any case starts, I think we're now close to 100 checks are being performed on all the different parameters that the user can enter. And from manufacturing perspective, for instance, a very common one that would stop a case is if a user enters a minimal size which is unreasonably small. So, for instance, that it would enter a design resolution in the order of a micrometer or smaller, which from heat sink perspective and manufacturability perspective has no meaning at all anymore. So, and then the case will not start and will simply say, your smallest feature size is way too small, please enlarge it. Those kind of checks are done. Really cool. Yeah, thanks for giving us these insights. So if we take a step back and talk about Coldstream itself, you talked about global optima, and maybe can the user also give himself or herself different designs, so they know it might not be the only design you get out of Diabatix or like Coldstream, the Coldstream platform. Can you give like 5, 6, maybe 10 different designs? Is that possible, or would you have to rerun the simulation?
Yeah, you will have to rerun it. Right? So you have to really understand that if you do one design run, it's not sampling based. It's a gradient optimization based. So you need to change something either to the starting point or to the way the gradients and the data is interpreted to get to a different result. And it's not that you can derive one result from the other. So it's not that one optimization will end up with 5 or 10 different results that the user can pick from. No, it will just result in one design, which is then, to the understanding of Coldstream, the best design for this given component with the given boundary conditions. Typically, that's enough for users. Now, we do have some customers that were experimenting, for instance, with different materials or with different manufacturing settings. And for them, what we did include is the option to design at conceptual level. So then we don't proceed to the full manufacturable design all the way at the end at high resolution, but basically we run the design cases run at a lower resolution, not all the way to the end of the design run, but stop somewhere in the middle. Once the thermal performance is more or less stable, and that result is then sent back to the customer so that he can basically evaluate at lower cost a few design choices that he still has to make.
I see. When it comes maybe to the parameters that you can tweak, how many parameters are possible? When different pressure drops, I don't know, heat transfer coefficients, things like that.
Yeah.
What can you vary as an engineer? How many parameters?
Well, basically those that you need to set for your boundary conditions. So, for instance, if you have a heat transfer coefficient somewhere at the surface, in principle you could change that. But of course, typically that's physics that will, or your context that will determine what the heat transfer coefficient needs to be at a certain interface. But from design perspective, I think the most common changes that users typically make are either from manufacturability point of view, that they want to evaluate, am I going to CNC mill a component, or do I have a lot of advantage if I would 3D print that the same component, but then you get different shape out of Coldstream, or material choices. That's also a pretty common one, and that we see, or different loading conditions. So if you have multiple heat sources, which potentially do not operate all at the same time, you do get different heating configuration or loading configurations that they would optimize for each of those and then see what the differences are in designs. But we try to minimize, we really try to minimize the number of the amount of buttons that users have to make it as useful and usable.
User-friendly.
Yeah, as user-friendly as possible. So, for instance, after we launched the first version of Coldstream in April last year, the first 6 months, we actually removed more buttons than that we added buttons. Although the functionality of Coldstream increased during those 6 months, and that's really the philosophy that we try to introduce. So, from optimization perspective, for instance, user have options to include a target, an objective, minimize temperature uniformity, or put a pressure constraint or a temperature constraint, like this component cannot be warmer than 300 degrees Celsius, or the pressure drop should not be higher than 2000 Pascal or something like that. And there are some weighting factors in the objective that you can play with. Okay, it's more important that the temperature is low rather than that the temperature is uniform, but that's about it. So it's really, for us, really a matter of just entering the way you would like it to be, rather than trying to figure out yourself what the best configuration is for the different options, because that's actually what's happening in the backend of Coldstream.
I like that. I also like the usability aspect that you talked about. Is it also that engineers would be able to set some numerical settings, or is it really in the back end that's happening in the back? Yeah. That's good, because sometimes you get a bit confused as an engineer. Okay, what do I use now in terms of numerics?
No. So numerical schemes, that's all magic that happens in the back end. Okay. It's all full second order, the way we calculate. So that's then really our PhD engineering heart, where we say we want to make it as accurate as possible. But there again, we had the advantage of the focus that we have put into Coldstream. We know it is about heat transfer. We know the flow regimes, and that also makes it possible to set a very decent configuration for the numerical schemes, for instance. And the same with the meshing. There is automatic mesh refinement in the backend. There is automatic boundary layer meshing. All of that is done. User doesn't need to configure anything in the backend, anything for it. And does frustrate some users. So some users do ask it to have that option, but it is basically done in the backend. There's only one exception for it, that actually was a result from the test panel we installed prior to the launch of Coldstream, we do let users select the turbulence model. While also that is something you can actually perfectly automate in the backend. I mean, there are very good rules of thumb that indicate which turbulence model you can actually should be using. But from the test panel that we installed, basically was a set of existing customers, quite a few of them requested to be able to select either K omega or K omega SST or K epsilon. So that we added, but it's just a selection box, but the different parameters within each of those models, they cannot touch it.
Okay, don't tell me it's like a dummy button where people select K
No,
epsilon.
No, it's not a dummy button, but it is one of those settings that is also checked in the backend. So, for instance, if you would set laminar as turbulence and the case would be turbulent, user will get a notification.
That's
hey,
cool.
We think you made a wrong mistake. You made a mistake there. And the same with the turbulence settings. If some settings are checked, that the user will get a feedback like, hey, I think you chose this turbulence model, but check our documentation because I think there's a smarter option to make.
That's pretty cool. Yeah, I like that. That's really cool from a usability perspective. I was also wondering, when you upload the CAD, is it also that you have some CAD capabilities inside of Coldstream, or is it in such a way or done in such a way that you upload the CAD already with the surfaces where the heat sinks would be? So you have to actually do the CAD pre-processing outside of Coldstream.
Yeah, indeed. And we have some, we have a number of plugins available. So, for instance, for Autodesk Inventor, that you can directly upload from within Inventor, send all the data to Coldstream, so that you don't have to manually export to a step file first and then upload it again into Coldstream. But the philosophy there was the same as with the post-processing. Our core expertise is in the generative design and of the components itself. We're not CAD experts, or we're not a software company developing a CAD tool, and we're not a software company developing the best post-processor, but we're a software company developing everything that comes in between when it comes down to the generative design for the heat sinks. So from the CAD perspective, there are a few things, a few features that are in the pipeline that probably will be added in the near future to make it somewhat easier for the user if they would have, for instance, forgotten to indicate a certain surface as a boundary, or if they forgot to upload the design region or something like that. So to simplify that a little bit in case they made a mistake. But we won't go as far as for instance, what SimScale has done with one of their latest releases, that you have a fully integrated platform. Because for us, that's a little bit against the nature of what we want to achieve with Coldstream. We want to basically enable the engineer to give things out of hand and trust the software to do that job for the engineer. And you cannot do that if you add too many buttons in the platform, because an engineer will press all of them.
That's true. I feel guilty now. You exposed me in the podcast. I was wondering also regarding the black box approach. So some people would call it the black box approach. So you don't have a lot of buttons, a lot of stuff, calculations happening in the back end. Do engineers sometimes like that? Of course, you talked about the turbulence selection and laminar turbulence and whatnot. But do some engineers feel, no, I want to be like a coder and do a bit of hacking in the platform, or do it all myself? Do you see that sometimes as a bit of a pushback?
Yeah, well, of course, engineers. I mean, I know how I am myself. It's you want to understand everything that's happened to the maximal extent, and the idea then that you need to see those parameters and those buttons that you can press is one of those things that could help you. We feel that. I mean, we do get that feedback, or we do get that questions about it. Now, if users have a question about, okay, what's happening in the backend, or what are the parameters that are set, etc., we're typically very open about it. Our secret sauce, we will never reveal that. But when it comes down, for instance, to the numerics or to the meshing or whatever, I mean, for instance, the mesh, if they want to see it, you can download it after the simulation is ready. It's in the VTK data, for instance. So we try to be open, but if adding a button means that it becomes less usable, Coldstream for the general user that we're aiming for. And really keep in mind, you want to be able to give the CFD expert the capabilities of the CAD engineer and the CAD engineer the capabilities of the CFD expert. If either one of those two are endangered by adding a button, we will not add that button if it's not needed. And I cannot exclude that at a certain moment there will be an expert mode that some people would see, the expert CFD users, for instance, would see a few more buttons. I'm not going to exclude that, but then it will be still hidden for the general user.
Talking about expert mode, is there also an API that people can work with yet, or is that?
There's an API available. Yeah, and there's also, for instance, what we use to couple to the CAD tools, and we use the same API to couple to our supercomputers in the backend. So it is available. So if people are interested in developing a plugin or a coupling with their own tools, we're always very open to discuss that.
Great. Also, when it comes to, I was thinking about something else, which is who should actually use the platform, Diabatix, which is just a filler question because I had a very interesting question which I just forgot. So maybe talk about who should actually use your platform. Is it specifically larger companies, people who have thermal issue problems? Should they run to Diabatix and say, we need you?
Of course, everyone can use it. But we see two big user groups. On the one hand, the big tech multinationals. There we see those are companies very often have teams of 10 or 15 or 20 or even 100 thermal engineers working on developing new products and who are under a time pressure and a performance pressure. Performance pressure in terms of, let's take the example of an electrical car. I think everyone will know by now that battery cooling and battery thermal management is one of the primary issues when developing the battery pack. But of course, if you don't manage to find a solution in a matter of in the time span that is foreseen, then you actually risk the launch of your or the presentation of your new car. And so there is a time pressure to reach a certain performance. So especially for those people, that's actually was a starting point for Diabatix 5 years ago. But now with the launch of Coldstream, we actually managed to open it up also to those companies who actually don't have thermal engineers in-house and don't have those thermal experts and simulation experts, but who do have the CAD engineers in-house who do know how to draw their product, how to and are aware of, I need to foresee some cooling, but who don't necessarily know what the best practice is to design those heat sinks or those cooling components. And also for them, and actually we see that that's the group that is actually the growing the fastest within our user base, are those companies that don't have that expertise in house, but by starting to use Coldstream, instead of having to hire an expert thermal engineer in that field, they can actually hire a regular engineer. With all respect, of course, who has a notion about what is power, what is thermal performance, etc. And by giving them access to Coldstream, they can actually do the job then with their team, like what you would be able to do when you had 1 or 2 thermal engineers in that team. So it's really for both type of companies that Coldstream is very useful.
So then the question that I now had, and thanks for explaining this, by the way, is I was wondering about the when we talk about cloud-enabled tools such as Coldstream, do you feel that there's also a bit of a pushback? Because I had also other guests on my podcasts, and I was asking them the same question. Sometimes engineers or like companies say we are a bit afraid because you're on the cloud, but sometimes that's just an excuse because they don't want to go with the solution yet. Maybe there's some budget limits. How do you see that personally?
Oh, we don't have experience. We don't experience any problems at all.
Okay.
No. That's certainly with big companies. Well, we have a saying at Diabatix that there's no engineer as conservative as the R&D engineer. So everything that is new to him, they are a little bit afraid of. And especially with big companies where you have also people then in charge of which software to be used, etc. There it's even worse, because cloud, and it's like speaking about the devil. You simply don't talk about it. In some companies, you have, it's cloud. Oh no, then no, for sure not. Regardless what the functionalities are. So we do feel pushback from some companies. It's very often very region dependent. For instance, in Japan, we have far less pushback on it than talking about Europe. And the same with US. There, when we're talking about military applications, it becomes a little bit tricky because our servers are located in Europe. So there it's a little bit more complex. But in general, especially in Europe, that we feel that there is some pushback towards the cloud because of uncertainty about data protection. And I think it's also Europe that is most aware about data protection and data security, etc. But we try to build Coldstream as robust as possible and as safe as possible. So, for instance, all the data that we store, the user has at all times a full overview of where the data is, which server it is stored, what amount of data is, and there's a trash bin next to it. So the moment I want to remove it, it's gone. And it's all hosted on IBM servers, which have part of a user use the highest security level of that IBM has to offer, and that's I don't know the exact code, but basically we call it military grade storage. So there's nothing safer from a storage perspective than what IBM offers at this moment. So we try to make it as robust as possible, but even then, some customers simply say we cannot do it. And we had now one particular customer in France where the engineering director is pushing towards the use of Coldstream that hard that now their IT department basically gave in, and they came with a list of requirements for Coldstream, a number of changes we have to make it even more secure, and then it will become acceptable for them. And we're now implementing those changes as well to gradually make it introduce it into those big companies. The small companies typically don't make a fuss about it. They're much more agile from that perspective.
Interesting. So someone would be able to actually run it locally on their own machines if they would have machines. Is it possible, or is it?
No, we don't allow it. No, so we don't have a server installation available. For me, that's going backwards because I think all companies, even those big engineering software companies, all making the shift towards cloud solutions. I mean, Siemens does it, Ansys does it. SimScale is a perfect example of offering a cloud solution. So going back to a server, like a local installation and server installation, that for me feels like going backwards. Again, same answer a bit of with the expert mode. I'm not going to exclude it. So if we have sufficient reasons to move in that direction, we will do so. But at this moment, the potential of growing within the cloud environment is more than big enough not to go in that direction.
Interesting. Good. Got it. When we talk about the future, Lieven, 5 to 10 years, where do you see Diabatix and also the future of simulation in general?
Yeah. Well, future of simulation is it's I think easier to predict because simulation, I think everyone feels it is becoming more and more important part in the product development workflow, and the tools also become better and better at it and faster. Right? So the integrated workflows, again, I don't want to come back to the same example, but the movement that SimScale is making is, I think, a very, very good example of where the classical simulation tools are in the direction that they're moving. So where they started as a more traditional simulation tool, they now moved into extending it with CAD capabilities, and they're coupling it with optimization software, etc. So it becomes one integrated package, and I see that I only see that tendency I see only becoming more and more increasingly fast being implemented. And then combination with spicing it up with AI, etc., and machine learning to make those simulations even go more faster than ever before. That for sure will not change. But of course, from especially with starting Diabatix, what I do believe is that is an ending story, that simulation part. Because what I do believe is that at a certain moment, generative design will become the dominant way of designing components and designing products. And that simulation, where now you have whole teams of being full-time simulation engineers, that those teams at a certain moment will decrease in size again, because everything that they do today and that they are required to do by hand will at a certain moment be integrated into bigger software solutions. I think Coldstream is one example of it, but you have a whole series of others like Fusion 360, etc., who already do that for structural parts as well.
So maybe even when we think about DALI, that in the future, maybe if you go to the Coldstream platform, you type in the text as an engineer, I want to have a heatsink with this and this boundary condition, and suddenly you have like different heatsink designs that you could use. Yeah,
who knows? Yes. So we will see. So I couldn't predict 5 years ago where we would be with Diabatix today. We started as basically engineering consultants, moved into a service company. Now we're a software company. I don't know where we will be in 5 years, but what I do know is that over the past 5 years, the quality of the work that we have delivered and the quality of the software that we're developing is growing exponentially. So I'm really looking forward to see where we will be in 5 years and to see what the added value is that we can bring to the industry at that moment.
Definitely. Really looking forward to it, Lieven. And also, I think I've seen you 3 or 4 years ago when I was looking up a PowerView tutorial, then I saw Roxanne doing a PowerView tutorial. I'm not sure if it was 3 or 4 years ago, but it definitely was a long time ago. And actually seeing you grow like this, you have a new website, how it's made and what your product offers is really, really exciting. And maybe, Lieven, we have a kind of a demo on my channel in the future. Let's see if people are interested.
Yeah, definitely. And if someone wants to try, you can just go to our website. There's a try now button. You can, if you click it, you immediately get login details in your mailbox, and you can just log into a demo environment of Coldstream, and you can just see what it is about, and you can just click around and feel the experience.
I hear it, guys. Well, you're hosted on the cloud, so if there would be a spike in users just because of this podcast, you're on the safe side.
Yeah.
That's cool. I hope the people enjoyed it. Any closing remarks from your side, Lieven? Anything that we might have missed? Any last motivating words?
No, well, I think I wanted to thank you for this opportunity that you invited me and to speak about this. I'm really enjoyed it, and I really love what you're doing, and that you're bringing a whole community together and bringing on news and existing and exciting technologies from all different angles all together. So I really love being here on the show, and looking forward to a second invitation. So.
Thank you so much. Yeah, it was kind of a pain this morning for both of us, I think. Me overthinking if everything would work. I'm not sure. Maybe the audience can tell if the angles are perfect and whatnot. But I think it will get better over time. But you were the first guest on the first live session, so that's really
Hello, that's the honor is. It's almost too big.
Yeah, we can see in 5 years if the podcast is like 500,000 clicks or something.
Yeah, well, we will see.
Pretty cool. Lieven, thank you so much, and I wish you an awesome rest of the week.
Jousef, thank you.